Hello class and welcome back to Geology 1A, and today I'm going to look at the Topographic Maps lab. So in the Chapter 1 module, the lab we're doing this week is a Topographic Maps lab. So now we're here at the Topographic Maps lab for this semester, and I'm going to load these videos up today on September 2nd. And again, I've given you a couple of different options. You can download the PDF form or the MS Word form. And then remember, you want to download those and have them on your computer, but then you can print out the answer sheet, which are fewer pages, right? And they're actually the problems you'll be working on. And I've already downloaded the Topographic Maps file here, the PDF. On Macs, you can use Preview, and Preview allows you to edit a PDF. Or if you have Adobe here on PCs, and also I guess Adobe would work on Mac as well, you would go to the Edit, and then you want to edit text and images there, and then you want to click on this add text here, add text, and you can minimize this as well, and then you can go in there and start answering, or at least you can type in your answer. So if you're not printing this right now, you have trouble printing, you can type in answers here, although there's some pages at the bottom here where there are some figures that you do have to draw on. And I do have the hard copy as well. I'll show you what to do there. Okay, so for this lab, we need several tools. We're going to need a protractor and a straight edge ruler, and for measuring distances on the maps. For this first part, it's pretty straightforward. Remember the key thing, in fact, let's go over here to the document camera. So the key thing about the protractor, let's zoom in a little bit on the lab, is that you want to, you probably haven't used a protractor in a while, you have to kind of, this will be a little review on using the protractor here, because here they're asking us to measure, to draw a line between points A and B, and then B and C. So A, B, and up to C. So we can draw a straight line across here from B to C, and then they want us to measure that angle here, right? And so and determine the latitude of this. Really, it's just parallel. Remember, they're parallels of latitude. They're parallel because they parallel the equator, right? So what is the latitude of point C? And so to do that, protractors have this bullseye, right? So the bullseye, you want to put the bullseye right on point B there, and then align the horizontal here, or the bottom line here that goes through A, and you want to measure that angle up. So it's 10, 20, 30, 40. Make sure we get, so it looks like if I can extend this out, it's about maybe 44, 45 degrees. Let's just call it 45 degrees. So this would be 45 degrees. And remember, we're north of the equator. So every point on this line is 45 degrees north, right? So that's what it's asking us to do, right? So then you'll do the same thing for A, B, and D, but then you're going to draw the parallel down here for D, and you're going to measure that angle. In fact, let's just draw it in here. So you want to measure this angle, and then you want to write in, or at least put it up here as well, the latitude. Remember, this is going to be south down here, so it's going to be something south of the equator, right? So that's a little bit about on the protractor, and then as we go up to this next figure, actually, there's a question here, number 4. So here they want you to draw in. In fact, I was telling students in another class that let's not do the 80, because the 80 is so high up here that it doesn't even, you can't even put it in there. But let's do the 60. So what you want to do here is you take your protractor, right, and I put it right here, and then what I do is I'm going to make sure it's horizontal there, everything's lining up there. And then you want to go up here 20, 30, 50, 60, 70, we want to go 60, right? So if we could draw a line from here out to 60, it would go out in that direction. So in fact, I'd put a little tick mark there. Then I'm going to draw this line out up to there. So that angle right there is 60 degrees, right? And now I can draw a parallel up here at 60 degrees north. And then I know that everything at this parallel is 60 degrees north, right? So that's what you want to do for this problem number 4. Skip the 80, because 80 is going to be so little up there, it's going to be hard to even show up. All right, so the next figure here, the key thing about this one, you want to, in fact, I even say here for Yeah, do not use a protractor, just estimate. Yeah, so estimate the latitude, right? So do not use a protractor, just estimate. So for example, point F, so if this is 20 degrees north and that's 0, that's maybe, it's a little bit less than 10, maybe it's 9 degrees, right? So you, again, you're making an estimate. Make sure you put north or south, right? So everything down here will be southern hemisphere, everything up here is northern hemisphere, right? And then, so you'll just complete this table here. And then for Polaris, you know, I kind of talked about Polaris over here. Remember Polaris is the North Star, and the North Star is so far away from Earth that basically every line of sight, every point where you are on Earth is basically a parallel line. So these lines represent parallel lines because Polaris is so far away from Earth that when you see the star, you're essentially seeing parallel lines on this little tiny blue ball that we live on, right? Now, and then your local horizon is right here. So you would measure the angle from Polaris down to the local horizon. So if you measure 90 degrees, that means Polaris is straight above your head. That means you're at the North Pole, right? Your latitude is 90. If you were at the equator, you would see Polaris right on the horizon, and there would be no angle. So 0, you're at the equator, 0 degrees. So if you're measuring an angle of 60, you're at 60. So essentially, the angle that you measure is your latitude. So this is kind of a redundant question because essentially, if you measure 26, you're 26 degrees north, right? So remember, you could only see the North Star if you're north of the equator. In the southern hemisphere, we use the Southern Cross, right? Okay, the next bit here is about longitude. And so, you know, I talked about the prime meridian down here, the international date line. Remember, Earth rotates. The key thing to all this is it's 15 degrees per hour. So Earth rotates 15 degrees per hour, right? And remember, 1 degree is 60 nautical miles, right? Or 69 statuette miles, right? So those are the regular miles, 5,280 feet. So if we could do a calculation there, 69, now I'm going to do this math here because this question came up. So 69, because that's 69 times 15. So basically, what I'm telling you is that at the equator, you know, Earth is spinning, right? Earth is spinning around here at the equator, right? It's spinning, and it spins eastward here. It's spinning. So, and then remember, these 69s, it has to deal with these things called great circles. So great circles. So in other words, a great circle would be the full circumference of Earth, the 40,000 kilometers, 24,000 miles, right? It's the full circumference of Earth. So based on what I just calculated, Earth is spinning at over 1,000 miles per hour. That's how fast Earth is spinning, right? I was just reading a book about how to talk to science deniers, and the first chapter is about the flat earthers, right? And they just don't believe that we're moving, that Earth is spinning, right? Well, it's spinning, and we should know as scientists, or as you guys as budding scientists, you should know how fast Earth is moving. It's moving over 1,000 miles per hour, right? And all you got to do is put a stick in the ground where there's no shadow, and then wait a little bit, and you'll see there's a shadow because Earth is moving. And obviously, as you go farther north, it's moving a little bit slower, right? And as you're moving, because the North Pole, basically, you're at one point, you're just spinning around, right? And so I don't know if you guys ever heard of something called the Coriolis force. So the Coriolis force has to deal with different parts on Earth that are moving at different speeds, right? Because the latitudes farther north, these are smaller. They're not great circles. The only place where you have a great circle is at the equator, right? So that's where you're moving at 1,000 miles per hour, right? Up here, I think I did a problem in my oceanography class. If you're up in that latitude of like Portland, Oregon, or New York, maybe a little bit north of New York City, you're moving at about 750 miles per hour, right? You can calculate this based on these 15 degrees. You can see the space here is smaller, right, as you go farther north, right? These 15 degrees of longitude here, right? So anyways, that's a little bit about the Coriolis force and some things you should know about. All right, so let's look at determining our longitude. And so here's another example where you're just estimating the points here, right? So that's at 15, C is at maybe somewhere between 30 and 45, maybe it's about 37, right? 36 degrees C. Remember, this is, and the other thing about the hemispheres, this is the eastern hemisphere, this is the western hemisphere. So make sure you put east and west on your data points here. I kind of skipped question number 7 over here. So for figure 3, you want to locate and label the prime meridian, right? So if we come back here to figure 3, let's call this the prime meridian. So the prime meridian is the 0 degree, that would be the 0 degree longitude, right? And then everything to the left of here would be the western hemisphere, everything over here is to the east. And remember, we pick the 0 degree longitude as Greenwich, England. And remember, Greenwich is the home base of the British Navy. And they're you know, think about Captain James Cook, you know, exploring the oceans in the 1700s, and all the sailors back in the 1600s. They were really, they charted the oceans, right? So they mapped the oceans and the continents, and so they picked 0 degrees as their home base, which is the British Naval Academy in Greenwich, England. In the past, you know, the hub back in the like the 100s, the 200s, you know, back in the time of Eratosthenes and some of the people in the Great Library of Alexandria in Egypt, they were making maps of the Mediterranean, and they were picking Alexandria in Egypt as a 0 degree meridian. So in other words, remember, every line of longitude, every meridian is identical because everyone's a great circle. There's no unique one. For latitude, the equator is unique, so we can pick that as 0. And then they get smaller going north and smaller going south. But for longitude, they're all great circles. They're all exactly the same. So that's why we have to pick one. And so we picked Greenwich, England. At least the British did, because they were charting the oceans there. And then now for this next question, they're asking us to sketch a couple of different meridians. And you can just do 2 or 3. So remember, you would go from the North Pole, and think of these like wedges in an orange, drop down, and then you'd go to the other side of the Earth and come back up. You could draw another one here. So come down, go back up. So that's all I'm doing here, is I'm just showing a couple of different meridians here on my figure 3. So you want to come back and do this figure 3. I think they ask, we did those, sketch at least, so I did 4 there, Western and Eastern hemispheres. Okay, so that's pretty straightforward. All right, so your figure 3 at the end should look something like this, okay? We did problem 9, you're gonna do that. And then, oh yeah, so now we get to the quadrangles, right? And in fact, I think I'm gonna start this on the next video because I'm only doing these in part here. So let's stop here for now.